All right, so here we are, and we're going to take a look at our first sample problem. So we'll go through it together, we'll take our time, and hopefully it'll make good sense to us. All right, let's take a look. So the centers of two uniformly dense spheres are separated by 50 centimeters, and each sphere has a mass of 2 kilograms. Calculate the magnitude of the gravitational force of attraction between the two spheres. So this is a pretty straightforward question. We know that our first object, well, first let's draw it, I suppose. We have a sphere and a sphere, and here we are. And we can say that the mass of the first sphere is what? 2.00 kilograms. And we can say the mass of the second sphere is 2.00 kilograms. And we can say that the distance between them, r for radius, but it's kind of annoying we don't just use d for distance, is 50 centimeters. Now, how do I write 50 centimeters in SI units? Because, of course, centimeter isn't an SI unit. You could do dimensional analysis. Or if you can just do it in your head, that's obviously great too. But nothing wrong with dimensional analysis. And that's going to give us 0.50 meters. All right, so there is our setup, and now we can just do our math. We can say the force due to gravity will be equal to G m1 m2 over r squared, and then we can actually fill that in. And so we know that that will mean what? Well, we know that mass 1 is 2.0 kilograms. We know that mass 2 is 2.0 kilograms. And we know the distance between them is 0.50 meters. Okay. So the force due to gravity then will be, remember we start with G. And if you can't remember, G, the gravitational constant, is 6.67 times 10 to the negative 11 newtons for every 1 kilogram system held 1 meter away from each other. So 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. All right. And we're going to multiply that by our first mass, which is 2.00 kilograms, our second mass, which is 2.00 kilograms, and divide it by our distance, 0.50 meters, but we can't forget that we have to square that. There we go. Whoa. Oh. I'd like to never see that again, all things being equal. And then we can do our calculation here. We can say force due to gravity is equal to 6.67 times 10 to the negative 11 multiplied by 2.00. Whoa! Multiplied by 2.00 divided by 0.5 squared. There's our calculation. I'm going to paste that in. Interesting. And I want to take a close look at the units, and we can note that the first kilogram will unsquare that kilogram down there. right? If we start by looking at units there, the second kilogram will do away with kilograms altogether. And then you can note that we have got meters squared down below. And that will cancel with meters squared up here. And that's going to leave us with only newtons as our unit. So we can say the force due to gravity in this case will be, and how many sig figs do we have? Looks like, oh, it was 50.0 centimeters. So that should actually be 0.500. So we have 3 sig figs. So this should be 1.07 times 10 to the negative 9 newtons. So you can see that if you've got small little objects, 2 kilogram objects, you know, not a lot of force here. Not a lot of force at all. You know, just a little bit more than the gravitational constant. Remember, the gravitational constant would be if your total mass was 1 kilogram, and if the distance between them was 1 meter. Here we've less the distance, so we get a bit more force, and we've done 4 times the mass, so we get a bit more force, but still a very small force of attraction. All right, good job. That's question